and share my screen. Probably should have shared the screen first. Definitely should have shared the screen first, but all right, yeah. So in rectangular coordinates, differential element area element comes from thinking about subdividing the region into little rectangles. Okay? But in polar coordinates, we're breaking them up into little polar regions, as you can see in the little diagrams here. Right? So it's the same, but it's different. It's really just kind of getting an idea of how we would equate one to the other. Right? So if we know that S equals R theta, then that little tiny segment, that little distance along that segment would be the product of delta R and delta theta. Right? So that's really what we're after here. And then we figure that out, then we're in pretty good shape. Right? So if we want that on an instantaneous level, let me get my glasses clean. That would allow us to create our multiple integral in order to anti-differentiate to get our solution. Right? So on the next page, we talk about how we get from one to the other. And this is the classic definition, the derivation of the polar multiple integral formula applying to the Fubini's theorem. But what we're going to do is we're take kind of a different approach. If I can get my my screen to work. So what we're looking at is well, previously that rectangle, that rectangular area would be determined by the product of dx and dy. All right. So what we want to do is somehow convert that into r's and thetas. And we will. It's just going to take a little doing because we know that x is equal to r cosine theta and y is equal to r sine theta. This is all going right back to the first unit. So differentiate dx d theta. I'm going to need a little bit more room, so let me move this out of the way for the time being. Dx d theta first r times the derivative of the second times negative sine of theta plus the second function cosine theta times the derivative of the first dr d theta. Okay. Clean it up, move some things around, multiply through with the d theta. So multiply everything by d theta. We get dx equal to negative r sine theta d theta plus cosine theta dr. And we do the same thing with y. All right. So y is equal to r sine of theta. So dy d theta, first times derivative of the second, r cosine theta, plus the second function, sine theta times the derivative of the first. Clean it up, clear out the d thetas by multiplying through. And we get dy is equal to r cosine theta d theta plus sine theta dr. So what we're looking for is the product of these two things. So I want dx dy. Okay. So that's going to be the product of this and this. We're going to have to move some things around, resize a little bit. So a little algebra. We distribute out. Use my highlighter. So r squared, sine theta, cosine theta, d theta squared. The outers tends to get a little messy, but that's all right. It's all part of the fun. We're looking at minus r sine squared theta d theta dr.
Professor?
Question. Yeah.
Isn't that a negative r squared?
Negative r squared. Oh, for the leading one. Thank you. Yeah, good catch. All right. And then inners. We're looking at r cosine squared d theta dr. So, you know, kind of running out of room, so I'll just tack it on here. R cosine squared theta d theta dr. And then finally, do this in different color. Product of this one and this one. Sine cosine dr squared. Okay. So plus sine theta cosine theta dr squared. It can be, like I said, a little bit of a mess, but I also said that's part of the fun. All right. So that's all equal to dy dx. All right. So we kind of have a little bit of a conundrum on our hands, but it'll clean up. It's just kind of weird to think that it would. All right. The first thing that you may notice has more to do with the trig functions than anything else. All right. And so if we can kind of wrangle a completion to that, then we'll be in pretty good shape. But also, we want to get to a point where we can just wholesale cancel things, because somehow this is supposed to clean on down to r dr d theta. Right, so that means all the sines and cosines are going to go away. All right, and it all comes down to this. It's kind of a basic idea. So let me draw the diagram somewhere over here. I'm going to bring it in. All right, so in an ordinary circle, unit circle, you'd have some angle, theta, if I can make a theta, the opposite side of which would be y, and the adjacent side of which would be x. All right. So we've kind of changed that idea to say, all right, well, we're not really dealing with theta dy and dx. What we want is some infinitesimal change in theta. But that would still correspond, it would still be some measure of theta that we would be looking to minimize. All right. But it would be corresponding to an instantaneous change in y as it applies to x. All right. So what that means is that we have all those relationships that exist, the sine function, the cosine function, and so on. All right. But if we want to minimize our dy, I want my dy value to be reduced. I also want to minimize my dx. I want to reduce that. I want to shorten that length. Then what's naturally going to happen is that theta will approach 0. All right, so that's a key ingredient there. So if I want to have a minimum or an instantaneous measure as it applies to x and y, then the theta value would have to approach 0. So what I can do is I could find the limit. If I'm looking for the smallest, if I want to have the limit as theta approaches 0, I can apply that to the entire expression on the right-hand side. All right. So I'm applying it to both sides. It just doesn't seem really obvious on the other side. Right. But what you can actually say is that the limit as theta approaches 0 of x, y will become dy dx, or dx dy, sorry. All right, that's where that diagram, that explanation related to the diagram comes into play. If I find the limit on one side, I'd find the limit on the other side as theta approaches 0 of all of that stuff. So I wanted to, okay, well, whatever. Let's do it this way. So everywhere there's a theta, I pop in a 0. And in some cases, it just zeroes the whole thing out, which is great. Right? That happens for the first term, the second term, and the last term. Anywhere there's a sign, it zeroes out. So all I'm left with is r times the cosine of 0, which is 1, cosine of 0 squared is 1, r dr d theta. So I get my relationship r dr d theta. That's what dx dy is equivalent to, and also dy dx. Right, so it definitely takes a little doing, but we get there. That limit key, it being the key to the whole thing. Right. So we have an example that follows that talks about using polar coordinates to evaluate an expression, but I think might be a little premature. We should probably go back and tackle that problem that we did or couldn't do or didn't want to do using rectangular coordinates and see what we can do with polar coordinates. All right, so That's on the, I believe it's on the previous page, maybe 2 pages ago. 2 pages ago, maybe even 3 pages ago. Yeah, on page 76. So, that didn't snap into a line because I didn't use a line tool. So if we want to go this route here, there's a couple of ways to handle it, but the first and foremost would be to say, okay, so we have a double integral. It's written as a rectangular coordinate system, or it's written, sorry, in the rectangular coordinate system. So what we want to do here is convert it over, all right? So let me get this guy down here. All right. So we have a couple of expressions here that can be converted over. First and foremost is our, let me get the orange marker out, y equals. So we'll start with the bounds. We have x equals also. So let's focus on, we'll work inside out. All right. So I'll just jot down everything that would need to get converted over. So we have z equal to the square root of all this stuff. I have y equals the square root of 1 minus x squared. We got y equals 0. Then we have x equals 0 and x equals 1. I'll do the 1 first. So it's kind of keeping it consistent top down. Not that it matters. No. Let's do this real quick. So z equals the square root of 1 minus parentheses x squared plus y squared. Just going back to unit 1, we have some rules that we can work off. Those rules involve converting from rectangular form to polar form, and that's kind of the point of the whole thing. All right. So if we can apply those rules, then we're in really good shape. All right. So let's do that. Z equals the square root of 1 minus r squared. And since our goal is to get it exclusively in terms of r, we're right where we want to be. So check, I guess. Step 1 accounted for. Now we want to go the rest of the way. All right. So I can, if I wanted to, I can swap out my radicand integrand right now, but I don't. So what we want to do is handle our bounds. So I'll take care of that now. So I see we have y equals the square root of 1 minus x squared. I can square both sides. So y squared is equal to 1 minus x squared. I can add x squared to both sides. And so I get x squared plus y squared is equal to 1. X squared plus y squared is equal to r squared. And so r is equal to 1. All right, so that's a circle with a radius of 1. Could be -1 also, but we want to focus on just it being the positive. We can work off of that. Y is equal to r sine theta. So r sine theta is equal to 0. We can solve this for r, but really when you solve it for r, you're not really doing much of anything except for dividing out the sine of theta, right? But it is a product of two factors. So if I divide, I'm going to lose a solution, so I don't want to do that. So I can set each factor equal to 0, r equals 0, sine of theta equals 0. Now r equals 0 is the pole. The line y equals 0 is not the pole. Right? Line y equals 0 is the horizontal axis. All right, so that one, this one doesn't make any sense, or it's not helpful. All right. So what I would want to do is find the inverse relationship. Right? So inverse sine of both sides, theta is equal to the inverse sine of 0, which would be, it could be 0, could be pi. Any multiple of that, right? Anything along the x-axis. Right? So we're going to have to hold that thought and see where that takes us. For x equals 1, same general principle. So r cosine theta is equal to 1, except here we really can just divide out. If we want, we could divide out the cosine theta. But you could also go to factor it. You know, that's perfectly fine too. All right. So, you know, like you try to do that though, and you don't have the zero product property at your disposal. So that poses a little bit of an issue. Right? So we're kind of stuck in that regard. But what I could say is that r is equal to 1 over cosine of theta. And just kind of hold that thought. And x, well, theta is going to give me my value when it's a line on the axis, horizontal or vertical axis. In the case of y equals 0, it was 0, pi, 2 pi, 3 pi, whatever, and all the negative counterparts. This would be the vertical axis, so we're talking pi over 2. We can kind of cut to the chase on this. Pi over 2, 3 pi over 2, and so on. Right, so all this information is going to help us figure out our bounds. So we're kind of in a good spot here. Right. So now it's a matter of getting to work on it, you know. So I'm going to shrink this down a little bit, give myself some space underneath. All right, so I'm going to have a double integral. All right, it's going to be related to whatever the z function is. All right, so in this case, it's the square root of 1 minus r squared. I'm going to paste that in. Times r d theta. That's our substitution. All right, the innermost integral should have bounds that are function related. All right, specifically, we're working in the order of the r then theta inside out. So I would want to have an integral with bounds of integration that are functions of r. All right, so that's my orange stuff. My orange stuff is going to go from the innermost function or yeah, innermost to the outermost. All right, so it could go from 0, which would make sense. I need my pen. And then the outermost part, and so inner outer instead of bottom top, because when you're starting at the pole, you're working from the innermost part of the circle to the outermost part. All right. So the innermost part would be the 0, and then the outermost part would be 1. All right. Oh, and sorry, I underlined 0, but it was the wrong 0. It's this 0, r equals 0. The 0 to 1. So it turned out that that r value equals 0 was the relevant piece. All right. Because we're working in terms of r. Could have been working in terms of theta, so I had that information at the ready, but turned out I wasn't, so I didn't need that information. But I could have, so I held on to it. All right. Now we're working in terms of theta. All right, so the theta values, that's a little bit of a different story. We want this to go from 0 to 1, from x equals 0 to x equals 1. And we determined that that's going to correspond to an x value of 0. All right. I'm sorry, a theta value of 0 to a theta value of pi over 2. All right. So just to get a visual on this, we want to be thinking in terms of not only the position, but also the spin. So what I'll do is I'll just grab this diagram here that I have up above, and I'll just mark that up, just so you have an idea. Let me just move some stuff around over here. All right, so this is the base region. So if I want that first quadrant, right, because that's really what we're thinking about. We can go with all this computational stuff. It's all good. It's all helpful. But if we want to get down to business here, we really are looking for just this interval here, this region. Right? But when you're dealing with it in polar coordinates, you're looking at rings. Right? So that's what we're really focusing on. And what you'd ask yourself is, all right, so if I'm starting with the innermost ring, I'm going to be starting with an r value of 0 to the outermost ring, which is r equals 1. Now, if I want to cross-reference that, if you will, with theta values, I think I got my color scheme backwards here. Let me just do this. If I cross-reference that with my thetas, my theta value would start here. This is theta equals 0. And then work my way up, if it'll let me, through the region until theta is equal to pi over 2. All right, and so we'd have all of these other thetas along the way. But that essentially gives you your set of bounds. So we could do it using the formulas, I overuse that term today for some reason, the functions themselves, but you got to get to a point, or at least start thinking of the instance where it's like, well, what if I didn't want to come up with the rectangular form first and then convert it over? What if I wanted to go directly to the polar form? Right? Getting a visual of the base area, getting a sense of where your start and your stops are in terms of r and then theta. That's pretty much the mission, right? And you could see how complicated it is to glean the appropriate information out from the available information that we have here, right? So, but I figured I'd take you down that road just so I can kind of expose you to that, because I see people try to do that all the time. Now, this compared to what we had before is much more anti-differentiable. Right? They're both anti-differentiable, but this one is something that is easily done. Right? So if I want to integrate here, and now I can. Before it was like, we need to know more math to do this. I have an r that's built into the model and the square root of 1 minus r squared. So that's your classic U substitution. Okay, so the antiderivative of that is pretty straightforward, but you can jot down the U sub if you want. All right, so if you do it like this, you can actually clean up a good fair bit of it, all in one shot. But that's neither here nor there at the moment. All right, so you look at what we have here and what we're going to need to get rid of, and you can see that it's going to work out pretty nicely. All right, so I'm at a weird angle here. So U to the 1/2 times, well, oh, that was so weird. I apologize. I'm sort of half asleep, but I'm also like not feeling 100% well. And also, I don't know, divided brain. I'm just going to keep throwing out excuses for my stupidity and hope one of them sticks. I don't know why. The U is just what's under the radical. Just got through telling you how easy it was, and then I screwed it up. Negative 2r, dr. You fool. The U in that case being me. All right, so negative 1/2 du is equal to r dr. All right. So negative 1/2, and we have a du here. We can rejigger the bounds here, so that instead of going from 0 to 1, it goes to whatever is appropriate based off of the U model. So U of 1 of 0, U of 0 is 1. Okay, so it's going to reverse the bounds. And it's up to you if you want to keep them like that. You can put it in the calculator too. It actually it works out. It's when you're dealing with polars, very often the case that the innermost set of bounds is not even necessarily a function in the way that you're expecting in rectangular form. Right? So you just pop it right in if you want. You could also use some of the properties of integrals. We can reverse the bounds of integration as long as we negate it. Increase the exponent by 1, u to the 3/2. So 2/3 multiplied by 1/2. 1/3. Pop it in. You're looking at just a clean 1/3. And then I would integrate that over the interval of 0 to 2 with respect to theta. 0 to pi over 2, what I meant to say. Integrating 1/3, apologies, with respect to theta. And we're looking at theta over 3 over the interval of 0 to pi over 2. Okay, so we just pop it in. So pi over 6. And that would be our area, volume. So yeah, it takes a little doing, but it's possible. I think possible. Before it was, I mean, if it was possible, it wasn't something that was likely. So just getting it over to the appropriate form gets the job done. Now, integrating in a rectangular form isn't always something to be avoided. It's just in this case, there was a better way. So we used the better way. All right, so let's hop on back. I think it was page 78, 79, something like that. '79. So we're asked to use polar coordinates here to evaluate this integral, but we're given the function in rectangular form. Right? So we want to get a sense of what the bounds are telling us. Right? So we make a little note, and we use Desmos to support our work. So this is y equals. Now, it doesn't take much algebraic experience or knowledge to realize that those two radicals are going to give the same path. Okay? You could pop them both down. Let me just reset my screen there. So I'll type in y equals the square root of 4 minus x squared. It's the top half of a circle with the bottom half coming from the other expression. So in polar form, that's going to equate to a circle with a radius of 2, so just r equals 2, which is nice. You can also pop in x equals 0, x equals 2. Not much to see with the x equals 0, x equals 2. All right, so it appears that we're looking at the part of the circle that's between those two parallel lines. So the semicircle, I guess. All right, that's the base region. And we have some floating surface in space above it. All right. So that's where we're at. Get that picture in here. And I'm just going to accentuate the relevant pieces here. All right, so we're going to have a circular arc. I'll just do it by hand. That's increasing in radius. You. Oh, Lord of mercy. All right, we'll pretend those are concentric. All right. So we got that, and we just want to think about where that's going to, how that's going to span in terms of R. Smallest R in this universe here would be R equals 0. The largest R would be that outer ring there, R equals 2. Now, in terms of the theta values, it looks like we'd be starting down here at -pi/2. And then working our way out, up and over throughout that interval. Oops, so let me get back here. All right, and finishing off at pi/2. All right, so we have our theta balanced. Now we just need to convert this expression over into polar form. Easier said than done. Right. But just dive right on in. We know that x squared plus y squared is equal to r squared. I'll just make a note of it somewhere off on the side. We also know that y is equal to r cosine theta, r sine theta. So make those substitutions and we'll pretty much have what we need, at least to get started on this. Right, so integral going from -pi/2 to pi/2. Integral going from 0 to 2. Then r sine theta squared. Then r squared raised to the 3/2. And then instead of dy dx, r dr d theta. So then it's just a matter of a little bit of housekeeping. All right. So I'm get my two integrals. We're looking at r squared sine squared theta times, well, multiply the exponents, r cubed, r dr d theta. So keep the base, add the exponents. Oh, hey, that's weird. Oh, look at that. Yeah, so keep the base, add the exponents. We're looking at r to the 5th sine squared theta r times r dr d theta. So it's really r to the 6th if I combine steps. All right, so we're getting that from here, here, and here. So now I can integrate this using partial integration. Focus on just the r's and then bring in the thetas. So increase the exponent by 1, divide by a new exponent. So 1/7 r to the 7th sine squared theta. That's happening over the interval of 0 to 2. So that's 128 over 7. You plug in the 0, it goes to 0. So 128 over 7 sine squared theta. Now we're integrating that over the interval of negative pi over 2 pi over 2. And unless you want to get into trig integration, you know, the trig rules and all that, I would say just go right to the calculator at this point. I mean, you could have gone to the calculator sooner, I suppose, but now you really probably want to go there. So the integral, negative pi over 2, pi over 2, open them up, 128 over 7 sine squared theta you just type in the theta. You could just go with x if you want. And you get about 28.7 or so.
Do we have to do it by hand so we get the fraction?
No. No, decimal's fine.
Cool beans. Yes, that's all good. So about 28.7 cubic units. You weren't given any units here, so I'm just going to leave that alone, but that would be the solution. It's the bounds. The bounds make these kind of problems difficult. If you come up with the bounds fairly easily, then everything else kind of works out. Right? If it takes you forever and a day to come up with the bounds, then it'll take you forever and a day to do the problem. So that's that. Do another one. Cases where you have multiple functions, multiple surfaces, and we are looking for the intersection, or we have the intersection. Compute the volume of the solid formed by the intersection of the surfaces. Right? So there's a lot going on with these kind of problems, not the least of which is the diagram. You know, trying to figure out what on earth is happening. Right? So that's the big challenge. So first things first, let's get our z's into polar form. So z would be equal to r squared. Now this one you'd rewrite 5 minus x squared plus y squared, which in turn becomes z equals 5 minus r squared. All right, now we're looking at two paraboloids here. All right, they're parabolas that extend into the third dimension. So that part is all right. One of them faces up, the other faces down. Fortunately, the side view of a paraboloid happens to look very much like that of a parabola. And so if you're looking at it from the perspective, you know, where z is legit vertical, then your ordinary properties of parabolas would hold. Right? So if it's got a negative leading coefficient, it opens downward. If it's positive leading coefficient, it opens upward. Right? Whatever the lone constant is, it's going to be your y-intercept. Excuse me. Oh boy. So, yeah, whatever. So that's all well and good. I know which one is which. All right, the 5 minus r squared is going to be the downward facing one, so it's going to be a cap to the whole thing. And the z equals r squared is going to be the upward facing one, so it's going to be the bottom end. Fair enough. Now, as far as the bounds are concerned, I would want to know how far outward we're allowed to go. That appears to be based off of this, I'll highlight it, this ring here, which may or may not be circular, but it does seem that this is the furthest extreme, the outermost part of this function. Right? So if we can come up with that relation, then we'll be onto something. All right. So what we can do is set these two equal to one another, because it is the intersection. So r squared is equal to 5 minus r squared. Get everything over to the same side and factor. Well, maybe not. 2r squared is equal to 5. Better to solve for r squared. So r squared is equal to 5 halves, making r equal to, we could say plus or minus 5, the square root of 5 halves, but again, we know that that's just giving us a path around whatever the figure is. Okay, so it's a circle. We got our circle. It's going to be centered at 0, 0. We're centered at the pole, and it's going to have a radius of the square root of 5 halves. All right. So if I wanted that on Desmos, then I guess I do. I could plot it a few different ways, but I could, you know, if I want to work with it in rectangular form, I could just say x squared plus y squared equals 5 halves. Yeah, we can get the image that way. We could also convert it over into polar form. What did I just do? Oh, okay, well, I'll log in, I guess. Huh. Oof, I don't even know what I hit. Range. I think I might have just hit the back arrow. That was strange. So we can get it that way. Either way, the benefit of using Desmos, or another benefit, is that it flat out tells you the domain of the figure that you're working off of. Right? So here I'm looking at the circle. All right, so we got our circle, but I also have the model below it, so I'm just going to hang on to that. It's there. Now it looks like I want the whole thing. All right, I'm not going to draw the rings here. It's just going to be a disaster. So what I'm going to do is I'm just going to kind of just shade it all in. All right, so it's going to be a whoosh, 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 whoosh. A lot of whooshing. But then in terms of the angular measure, it appears that we are starting at 0 and going to 2 pi. So you work your way around in terms of theta. I'll just get a few in. You know what? It just occurred to me the rings were already there, so I probably didn't even need to shade it. Okay, so we're working our way around. So we got what we need. I got my r's going from the innermost value of r, which would be 0, to the outermost, which would be the square root of 5 halves. And then my thetas are going from 0 to 2 pi. All right, so now I just need an expression that represents the bounded region. Yeah, well, just like in two-dimensional, if you want to find the area between, in this case, the volume in between, you find the dominant function and subtract from it the non-dominant function. So in this case, double integral going from 0 to 2 pi. Going from 0 to the square root of 5 halves. But now I want to take the 5 minus r squared and subtract from it r squared. So it's the difference between the z's. Z top minus z bottom, if you like shortcut rules. Times dr dr r dr d theta. So clean it up. 5 minus 2r squared times r, dr d theta. All this stuff is coming along to the right. So 5r minus 2r cubed dr d theta. Increase the exponents by 1, I have a new exponent. 5/2 r squared minus 1/2 r to the fourth. And that's going from 0 to root 5 over 2. And computationally, it's not terrible. So 5/2 times the square root of 5/2 squared is 5/2 minus 1/2. Square root of 5/2 squared is 5/2 squared again is 25/4. All right, so we want a common denominator. So let me just multiply this one by 2 over 2. That gets us to 8. So 20. Oh boy. All right, so 25 times 2, so 50 minus 25 over 8. All right, and so I need to integrate that over the interval of 0 to 2 pi with respect to theta. So that's 25 over 8 theta over the interval of 0 to 2 pi. So pop it in, we're going to get 50 pi over 8, reduce it, 25 pi over 4. That, like I said, takes a little doing, but a lot of the things that are familiar about integral calculus are still kind of in play. So the next one has a similar look and feel. So what I'll do is I'll just throw a star on that one. So you can practice that on your own. Poor quality star. Try that again. There we go. A little bit better. Just debating how much I should do without it being overkill. Put a star on number 4 also. I mean, I'll do them all eventually. It's just a question of tonight or Wednesday. Debating. Okay, yeah, let's do number 5 together, because after that it's triple integrals. This one is kind of unique because of what we have to do in order to come up with a solution, so might as well. So we have x squared plus y squared minus z squared. I'm just going to jot that down over here. Equals 1. And that's happening over the interval of -2 to 2. So I need to do a couple of things. One, I got to find the bounds, but I also have to kind of get an idea of what the hell the question's even asking. Inside the hyperboloid of one sheet. All right, well, that figure, just to answer the question that might be out there, that figure is the hyperboloid of one sheet. All right, so I got that. All right. In terms of a polar form, it's easy enough. This is r squared. minus z squared is equal to 1. If I clean this up a little bit, I get z squared is equal to r squared minus 1. And then square root both sides. Z is going to be equal to plus or minus the square root of r squared minus 1. So we got that part. That's all well and good. Now, if I were to just integrate this, that might pose a problem, because it's like, well, what am I getting by integrating? And it's the same idea when we did volumes of revolution in Calc 2. All right, so you're going to have kind of a reason for why you're integrating. So what you're going to get is the volume below the surface. And below, and we know this from Calc 2 also, below is kind of an overused misnomer. It isn't really below. It's more like between. So the volume between what and what? Oh, I thought that was going to do it. So it's between the function and the given axis, whatever the axis happens to be. All right. So in this case, it's not an axis, it's a plane, but it's still the same idea. All right. So we're looking at, I just can't get this thing to look halfway decent. I don't know. Good enough. So what we're going to get when we go to find volume, we do it the right way, is we're going to get all this stuff. All right. You're going to get all this null space. We don't want any of that. All right. And it would be kind of capped off based off of wherever the XY plane is. All right. So between the top surface and the XY plane, if I only work with the positive Z value. If I work with the difference between the two, I'll get it all. But if I'm looking for the difference, if I'm looking for the volume contained within the hyperboloid, then what I would be looking for is the difference between that volume that we come up with, what I just shaded in red, and the volume of the cylinder that encapsulates the whole thing. Okay, so we got a cylinder here. This whole thing is a cylinder. It has its own volume. If we figure out the volume of that cylinder, and volume of a cylinder is pretty easy. The circle with height, so pi r squared h. If we get the height and we get the radius, then we'll have the volume of the cylinder, and we just subtract what we get for the volume of the null space from that cylindrical volume, and we'll have what we need. All right. So that's our mission. Fortunately, they kind of give us a sense of the volume. They said that this thing only goes from z equals -2 to 2. So that tells me that the overall height is equal to 4 units. We just need to pull from this the radius somehow. All right. So what I can do is I can work off of what I have. Let's take this guy. If I want the radius of the whole cylinder, then I would want to know the equation of the circle when z is equal to 2 or -2, doesn't matter. So x squared plus y squared minus 2 squared is equal to 1. So x squared plus y squared is equal to 5, which means that the radius is equal to the square root of 5. So now I have the radius. All right. So I can get the volume of the cylinder. I can do that right away so I don't forget. Pi times rad 5 squared times the height, which is 4. So that's 20 pi. Okay, so I'm good there. Now I need the hard part. All right. So what we can do is just get the top, just focus on the top. So I'm going to draw a horizontal line there and just ignore the bottom. We'll just double everything up later. All right. That allows us to work with one integral. So top half z equals the square root of r squared minus 1. Now, in terms of bounds are always going to be tricky, but it seems like these are another set of circular bounds. All right, so we're in pretty good shape here. In fact, I don't really need to do much to the previous example in order to get this one. The outermost part of this function, or this solid, is based off of r equals the square root of 5, which goes from 0 to 2 pi because we're not restricting ourselves from going around the entire circle. We want the whole shebang. Okay, so I can get my double integral going from 0 to 2 pi, going from 0 to rad 5, focusing only on the square root of r squared minus 1, r dr d theta. All right. Now, I mentioned this before, but I never actually did it. I was saying that for these problems, you could jump right to the calculator right away. That's kind of the beauty of it, right? Because they're single variable functions. So function, miscellaneous, antiderivative, root 5, r, so x, square root of x squared minus 1. Close them up. Oh, not that one. That one. dx. Oh, undefined. I am surprised by this development. What did I screw up? Interesting. 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 Oh, it is undefined, you schlemiel. Yes, you can go directly to the calculator. Yes, it's also important that you type the right stuff into the calculator. Yeah, 0 is not the, yeah. I'll explain why in a sec. The lower bound isn't 0. All right, you get a break in the expression if that's the case, because anything less than 1 is not going to cut it. All right, so if we look at the function, the domain, and I'll just jot it below, move this down. It has to be anything bigger than 1. All right, so r squared minus 1 has to be greater than or equal to 0, which means r squared has to be greater than or equal to 1. Take the square root of both sides. Yeah, we get some negatives in there, but it tells us that r has to be less than or equal to -1, which I don't care about, or r has to be greater than or equal to a +1. Okay, so that makes the lower bound here the +1. Well, fortunately, Desmos helped me out there. Hey, it's fractionable. That's good news. 8/3. D theta. The rest you can actually do by hand. Usually I go the other way. You know, you say, you know what? Let's let's do a little bit of work first, then go to the calculator. Now we're going to the calculator to do a little bit of work on our own. So 8 theta over 3, going from 0 to 2 pi. So we're looking at 16 pi over 3. All right, now again, that's the top half. That's only the top half. All right, so I need to double that. 32 pi over 3. And then I have to subtract that from the volume of the cylinder, minus the volume of the null. So 20 pi minus 32 pi over 3 is really 60 pi minus 32 pi, so it's 28 pi over 3. All right, so there's an order of operations here, but if you play it out and you avoid careless errors like I didn't, then you get where you need to go.